I'm back, na 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 na. Honors Physics Lesson 1.6 Displacement with acceleration. And look at it's Maximus. All right. So far we've gone through our constant velocity equation. So these two is when we have velocity that is constant, or if we're looking for average. And they work great. But what we introduced in the last two sections is this thing called acceleration. So remember, acceleration is change in velocity. So this is changing, which means that the amount of distance you cover will change as well. And that is due to our uniform acceleration. So we're just going to cover uniform or constant acceleration in this course. If you want to see change in acceleration, I'm sure you could find all kinds of stuff on it. All right, so acceleration tells us how fast the velocity changes. So what we're going to do is look at these equations over here. These are our uniform acceleration equations. And they're great for different things. This one you'll use sometimes maybe, but these two are going to be your bread and butter. You're going to use those two all the time. Get used to using those two. You might even use them together in the same problem to solve for one thing because they are that useful. All right? Okay, so let's go through some practice problems here. So how long does it take a car to cross a 30-meter wide intersection after the light turns green, assuming that it accelerates from rest at a constant 2 meters per second squared? So our acceleration is 2 meters per second squared. Our displacement is 30 meters, and we are looking for time. All right, so if you look back over here, we are not given time. So this is not going to help us very much. We're also not given our initial velocity, so that's not going to be very helpful either. What we can use is our displacement formula here and this formula over here, because the velocity initial is 0. So because it's 0, this part, I went a little crazy with my coloring here, this part of the equation becomes non-existent because anything times 0 is 0. And then if you have $5 and add $0, you still have $5. So we're going to use that equation. So delta x equals 1/2 at squared plus vit. And let's plug in some numbers here. So 30 meters equals 1/2 2 times squared, that's what we're looking for, plus 0 times time. All right, so again, this will just cancel out regardless of what time is, and that's good because otherwise you have to do that quadratic formula, and this avoids the quadratic. All right, so what this is going to end up as is 30 meters t squared, right? Because that's going to cancel out. 1/2 of 2 is 1. 1 times anything. All right, good. We're good. So then we're going to take the square root of 30, and we're going to get a time of roughly 5 point, it's like 477, so we'll say 48 seconds. All right, next one. Let's say you have an airport, and you are trying to design how long the runway needs to be. So you're going to accelerate from rest. So velocity initial equals 0 meters per second to a velocity of 27.8 meters per second. You're given an acceleration that your plane is going to travel at, which is 2.58 meters per second squared. You're not given any kind of time, but that's okay because you don't need it. what you do need is delta x. So you're going to go to this formula right here. 2a delta x equals vf squared minus vi squared. And that's supposed to be an f. It looks like an I, but it's an f, I promise. Okay, so 2 times 2.58 delta x, what we're looking for, 27.8 squared minus 0 squared. So we got, change color here, 5.16 delta x equals 772.84. Divide each side by 5.16, and delta x should equal 149.78 meters. Alright, so look at this one real fast. We have a baseball pitcher who's throwing a fastball, 44 meters per second, so velocity final, 44 meters per second. The ball accelerates through a displacement of 3.5 meters. What is the acceleration of the ball during the throw? So I'm looking for acceleration. Velocity initial is 0. It wasn't moving before he let it go. Alright, so same idea, same formula, only now we're looking for acceleration. And you should end up with 276.6 meters per second squared. That's one heck of a fastball. Alright, last one. Suppose a ball is thrown downward at a velocity of 15 meters per second. And this one might be very helpful if you're studying for that quiz that's coming up. Dun, dun, dun. Alright, so you're throwing the ball, the velocity initial is downward, so negative 15 meters per second off an 85-meter tower. Delta y, because it's going up and down, is negative 85 meters. It's negative because it's going down. What's the velocity the instant before it hits the ground? So I'm looking for its final velocity. I can also have another variable in here that is not shown. So the moment this ball is thrown, it's no longer having a force applied. So I'm no longer adding in any kind of acceleration. It would move at a constant velocity if something that we can't see wasn't pulling it down. And that something is gravity. So our acceleration is negative 9.8 meters per second squared. Something to remember. Alright, and we're looking for final velocity, so let's go ahead and plug some stuff in. So negative 85. Oops, let me rearrange this just a little bit. Not enough room. There we go. Alright, so 2 times negative 9.8, negative 85 equals velocity final, which is what we are looking for, squared, minus velocity initial, negative 15 squared, and we should end up with negative 43.5. Awesome. Okay. Hopefully this helped you out. I will see you next time. Sorry that it's a little long.